So we'll be presenting the average case complexity topic. This is Umang and Mohit on the other side. So let's begin. So the case for average case complexity. So previously in our course, we've looked at the time taken by an algorithm on the worst possible inputs. Like that is for when defining time complexity, we look at the time at which the algorithm will definitely halt 100%. However, in practice, we might have algorithms which have very different runtimes for different inputs. Like we might have algorithms that run very quickly almost always, but then slow down on one input. Then, based on our previous analysis, we would have put that algorithm down, say, like maybe the algorithm has like an exponential runtime on one input and like very nice runtimes on other inputs. Then we would call that we would like basically call that problem hard. I mean, using loose terminology, we would call that problem hard. But then again, like for the most part, it's and like given the distribution of inputs, that one bad input might just never turn up. So the algorithm might run very quickly almost always. So which is why I mean just doing worst case analysis, one might exclude the algorithm as an efficient one, but then we could have very nice average runtimes, which is why the notion of an average runtime might be useful to us. So, as it turns out, several NP-hard problems are actually very easy on many input instances and have a small expected running time. Of course, we're using the term expectation, so we need to formalize the distribution in which the inputs appear. So, for example, one sort of distribution is the uniform distribution on all strings of length n. So, all inputs appear with the same frequency. So, when defining a notion of an average case, we need to precisely make clear what we're talking about. So, we're basically talking about the complexity of a pair L and a sequence of distributions Dn, where L is the associated problem with language, and Dn is the distribution on a Dn is the distribution of length n. So we take for all n we have a different distribution. So with regards to this, we will make the following definition. Distributional problems. A distributional problem is basically a pair L comma D such that L is a language or equivalent distribution decision problem, and Dn is a sequence of distributions with Dn being a distribution on the strings on 0 1 of size n. So Dn is a random variable taking values in that whole distribution. So some examples are the Krieg problem on this distribution called GNP, which we'll define soon. Uh, the three color problem on the distribution GNP and the three sat problem on the distribution UML, which we'll also talk about shortly. So we can GNP is basically a way to generate a random graph. So GNP is a distribution on undirected graphs with n vertices. A random graph can be generated by randomly deciding which edges to include. So there are a total of n choose 2 edges, and for each edge we choose whether to include or exclude it with probability p. The obtained distribution is called GNP, and taking p equals half will give us the uniform distribution. So I mean we can sort of see why this is a decent model to input random graphs, because I mean if you think about it, like you're if you're if you're encountering random graphs, it's like very likely that you encounter some sort of distribution, and this is a very natural way to model that distribution. Of course, it's not this still is a certain restriction, and we can't use the word average for all kinds of graphs because we can have various distributions on the edges. Maybe some edges are more likely to appear, and like maybe the number of edges decreases as n goes up. We can have a lot of things, but basically this is a good model for a sort of uniform random graph. So given this setup, we can talk about the expected running times of algorithms now that we've sort of defined a distribution by which the inputs appear. So we'll just talk about some things that we won't go into these owing to lack of time, but three color has an algorithm which is linear time and very high probability when the inputs are sampled during GNP. Similarly, click and inset have algorithms which run in time and to the power 2 log n with high probability. Of course, it's more than polynomial, but it's much better than the 2 to the power n epsilon bound that we discussed in class. I'm not sure about that detail, but I'm pretty sure it was exponential. So moving on. So similarly, we can talk about the random SAT problem. So UMN is a uniform distribution on three CNFs having M clauses and N variables, where we obtain the distribution by, so for each clause, we pick three random literals for, so we have two n available choices of literals from the n variables and their n negations, and we take the disjunction of three of them. So and then we take the conjunction of all of them, and so we can see that as m goes up, we'll expect the fraction of satisfiable three cnfs having m clauses and n variables to go down, because I mean you're sort of adding more things, so it's less likely that things end up as, I mean the things are satisfied. So it's been shown that there exists constant C1 less than C2 such that if M less than C1n, and then the fraction of satisfiable CNS is very low, and if M is more than C2n, then the fraction of satisfiable CNS is very high. I think this should be the other way around, so we can maybe fix that. But let's move on. So now we move on to defining distP, the average case analog of P. So that's distP, like P was sort of used to capture the problems which are efficiently solvable. We want an analog, so we want something that's on average polynomial time. So we can start by trying a first definition. Given a distribution problem LD and an algorithm, define time A as the number of steps A takes on input X, time A X of course. So we say that a distributional problem LD is in dist P if there's a constant C and an algorithm A which decides L and satisfies the expectation of time A on X, where X is distributed as Dn, is order of n power C. So on first glance, this seems like a good definition. So we just replaced time taken by the expectation of time taken and bounded it by some constant c. However, there are some issues that pop up, as we'll see. So the first issue that pops up is that this definition is not robust to model changes. As we saw in class initially, if we change from a multiple tape Turing machine to a one tape Turing machine, we experience a quadratic slowdown. So depending on the distribution, we can have situations where polynomial time algorithms turn into exponential time algorithms on expectation because of the distribution works. So while doing analysis of complexity classes, the notion of a reduction, as we've seen, is a very powerful and important tool. And we'd want to define an average case reduction, like how we define all sorts of reductions in our course. We'd want to define such a notion, and we'll see that this definition is not very compatible with the notion that we'll define later on. So we can say that it's very easy to show that there's an algorithm A such that for every n, we have expectation of the time taken is less than n plus 1, but expectation of the time square is greater than 2 power n. So the time expectation of time is polynomial, but the time square expectation is exponential. So this is a massive problem, as we can see, because like we've just changed our computational model, that's what the square represents, and then suddenly it's all gone haywire. So let A be a problem where if x is the zero string, then the algorithm halts in 2 power n steps, else it halts in n square steps. So we make the distribution uniform. So the expectation of the time will equal 2 to the power minus n, the probability of the zero string showing up, times the time taken on the zero string, which is 2 power n, plus 2 to the power n minus 1 by 2 to the power n times n square, where n square is the time taken for all the other steps. So I mean, it's like definitely n square. So this whole thing is less than n square as a whole, less than equal to n square, it's order of n square. But as we can see, expectation of the square time is exponential because of this little 2 to the power 2 and that pops up. So moving on. So I mean, this is, as we can see, this is a very big issue with our algorithm because it does not respect model changes. So So, I mean, more generally, while dif- doing analysis on algorithms and making up new algorithms, we often would like a polytime algorithm. If we do it polynomially many times, we'd want the whole result to be also in polynomial time. But here, as we saw, just squaring the time causes issues. So clearly, this definition is not very nice, so to speak. So we'll seek a more robust definition for the notion of distP. And the change we have to make is very minor. So we just take the C from the order of n for C and then put it in the inside the bracket. So what happens is the expectation now we just take the Cth root and we say that the distributional problem is in dist P if there's a constant C and an algorithm A which decides L and satisfies this condition. So the expected time to the power 1 by C is less than equal to is order of n. So as we can see from the get-go, this definition does not have the square running time problem anymore. We can just multiply if an algorithm satisfies this for the time, we can just multiply c by 2 and then the time square will also satisfy that. So it respects model changes of that sort. And clearly there's nothing special about 2. We can multiply by any c by any constant to get an appropriate polynomial power and then the definition still holds. Also, so we can see that problems that take P is in a problem with in P is also in dist P. I mean, we know that dist P is actually a pair of things. So given an L and P and given any distribution of Dn, we have that L comma Dn is in dist P. This is because given L, there's a constancy such that every input instance takes time order of n power c. So the expectation of the whole thing will also be in n. So the time taken raised to the power 1 by c will always be order of n for all x. So the expectation will be order of n. So L comma dn is in dist p for all distributions n. All distribution sequences dn given that L is in NP itself. So another thing is that if there's an algorithm A which decides ln order of n power c steps on expectation, then we can see that L comma dn is in dist P. So we can use Holder's inequality to show that. So we know that by Holder's inequality, the expectation of something to a power is less than equal to the expectation of that whole to that power. So using this, we can clearly see that the expectation of the time taken to the power 1 by c is less than equal to the expectation of the time taken whole to the power 1 by c. The second expectation is n to the power c. So taking a cth root of that, we'll get order of n again. So anything that any distributional problem, any algorithm which decides a distributional problem for any distribution problem which satisfies the previous definition will also satisfy our new definition. So our new definition is a relaxation of our previous attempt. Another observation. Now you might think that okay, so we say that the expectation is order of n, but we might still have instances where we take a very long time. So by Markov's inequality, we can see that there's a high probability that the algorithm runs in polytime. So depending on like how large the input, how large the runtime is. Sorry. Depending on how long the potential runtime is, the possibility of the algorithm exceeding that runtime is very little as per Markov's inequality. So we can see that Markov's inequality tells us that the probability of a random variable being greater than a certain value is the probability of is less than equal to the expectation of that random variable times that value. So sorry, divided by that value. So we can see that here the probability of the random variable t time a, okay, on the distribution n being greater than t is equal to the probability of that whole to the power 1 by c being greater than t power 1 by c, which is less than equal to the expectation of time even power 1 by c times 1 by t to the power 1 by c. So this is equal to order of n divided by t to the power 1 by c. So depending on how large t is, it's that much less likely for the algorithm to exceed that runtime. which is something that we want, which is a very good thing to have. So right now we want to sort of formalize real life distributions, and we'll talk about why we're using these definitions. So given a string x and a length L, we'll define the cumulative probability as mu of dn, where dn is the distribution according to on strings of length, and as discussed previously. Mu of dn, we define it as the sum of the probabilities that dn equals y for all y smaller than x, where smaller than is defined by lexicographic order. So less than or equal to x, not smaller than. So we'll use this to define the notion of a p-computable distribution. We say that a distribution D is polytime computable if given n xt, we can compute mu dn on x up to t digit precision in time polynomial in n and t. So we can see that if we want a notion of, so you can argue that like, okay, if you want a notion of polytime computability, why are we doing this cumulative thing? But we can easily see that this restriction is just as strong as requiring the probability, the whole distribution dn to be polytime computable, since we can easily calculate p of dn, probability of dn equaling x, as mu of dn x minus mu of dn x minus 1, where x minus 1 is the string before x in lexicographic order. So if calculating mu is polytime, then calculating mu dn x is polytime in x, that polytime in n and t, where x is the n is of course the size length of is the length of x, then the same will hold true for n minus 1, for x minus 1, which is of length less than equal to l. So subtracting those two will give us the probability that dn equals x, and then that is polytime computable since both of these are. So now you might wonder why we're doing this thing, but we'll proceed with, before that we have some examples. So for example, the distribution the uniform distribution is polytime computable, where all the probabilities are just 1 by 2 power n, and then we keep adding that depending on the order of x, the position of x in the lexicographic order. And like many other distributions that are defined using explicit formulas are p-computable. So now we talk about why we use these definitions. So we're only looking at distributions that are polytime computable. This is because, so it's reasonable to assume that the problem instances we're taking were either generated by someone. So either someone's generating these instances themselves, or they're modeling some problem that is found in nature. So either case, since we're solving these things algorithmically, it's a reasonable assumption that at some point someone's inputting things into a computer. So if you're inputting things into a computer, you'd expect that whoever's generating the problem instances does not have infinite computing power. So So based on that, it's a reasonable assumption to put in the polytime computability restriction. Another reason is that we can come up with convoluted distribution. I mean, convoluted, not the technical term, just the like general language term, where distributions we can have where every problem is as hard on average as the worst case. So unless we restrict the kinds of distributions we can take, average case analysis will just be equivalent to worst case analysis, since we'll not get any new insights or results from this. So because we want to avoid that, we just don't want to reduce all average case things to the worst case things. We'll restrict the distributions we look at. So next we'll proceed to define the NP version of average case problems, and then we'll only look at distributions that are computable in polynomial time. Okay, so we now proceed to define distNP, the average case analog of NP. A distributional problem LD is in distNP if L is an NP and D is P-computable. Now we are defining this in this way because we want to basically look at the expected runtimes of NP problems, and then why we're using P-computable distributions we've already discussed previously. Some examples of these include the clique problem, which we clique 3-color 3-sat, which we all know are NP problems, and then we use the distributions GNP a GNP again, and then the uniform distribution scheme that we discussed previously, we use that those as the distributions. The uniform one is we can show that all of these are P-computable distributions, although we won't be going into those. All we need to do is be a little careful about how we're encoding the distribution, because like we said, the distribution is on n vertices, but there might be more than, like say GNP has NC2 edges, and we need to represent that. And we need to sort of be careful about the ordering to ensure NP computability, but we won't go into those details here. So now, since we've defined the class distNP, we will obviously start thinking about how it relates to distP. And it's sort of a little nuanced here because distP has all sorts of distributions, whereas distNP only has P-computable distributions. So the distP equals distNP question, although we won't be going into it, that's sort of, we only think about, we can only dist P is in dist NP is in dist P or not. So again, we won't be going into that. We'll mostly focus on how we can define reductions on this class of problems, and is there a dist NP complete problem. So later we'll see that that is the case. And moving on for now. So we want to define the notion of an average case reduction. An average case polynomial reduction, which we'll refer to as an average case reduction. Of course, since it's a reduction, we'd expect it to satisfy a few properties. If we have two distributions LD and L prime D prime, we'd want, if and f is a reduction, we of course we want this basic property that if x belongs to L, if and only if fx belongs to L prime, which is the basic correctness condition. We'll call this the correctness condition later on. So now we also want the size of fx to be polynomial in the size of x. This is the which we will call the regularity condition later on. And then if L prime D prime is easy, since LD is reducing to an easy problem, we want LD to be easy for whatever notion of easy we have. So let's see if just asking f to be poly time computable is enough. So if L prime D prime is easy, then so is LD. And then what happens? So we there if the notion of ease is captured by there being an efficient algorithm A prime for L prime D prime. So we let A be the obvious algorithm that we take an input X in L, and then the input is generated from the distribution D, and then we compute Y equals Fx, run A prime on Y. So is this an efficient algorithm for LD prime? Now, if this is sort of how we define reductions in class before for the worst case, what we refer to now as worst case complexity, but we see that there is a problem. The problem is simply that we might have, since we're taking expectation of something, we might have the situation where A prime is very slow on some input that doesn't appear very frequently according to the distribution D prime, but then as fx, when fx, however, might have a high probability of appearing. So this might sort of mess up our expectation calculation, and like we saw previously that square in our naive attempt definition earlier, where the squaring a thing becomes exponential, we might also have a similar problem here that it might pop up. So to prevent this from happening, we introduce the following condition, which we call domination. So the domination condition just says that for every string y in the set of strings of length Pn, where Pn is the size of strings outputted by f, we require that the probability that f of x varying as dn equaling y is less than or equal to, so qn, some polynomial qn, times the probability that d prime varying on strings p of length pn equals y. So why we want this, we can see that. So basically what we want is that if y doesn't appear very likely as y doesn't appear very likely, then if f of x equals y, then we also want f of x to not appear very likely. So basically we want that if y doesn't appear very likely from one distribution, then f on x, fx, if fx equals y, then the probability of x appearing is also very small. So the Qn is just here to make a polynomial bound, which will just make our calculations easier later on. I mean, we sort of allow a polynomial overhead in probability, but basically what we want is that if if fx equals y, where y varies as dn, then the probability of x appearing is also very small. This basically ensures that this whole problematic situation does not happen. Since like the probability of x where x can cause bad things, so to speak, is bounded polynomially by the probability of that sort of y appearing, where a prime is low on that y. So moving on. So now we get to the full definition where we say that a distributional problem LD average case reduces to a distributional problem L prime D prime. We denote this by the following inequality subscripted by A. If there's a polynomial time computable function f and polynomials p and q satisfying the correctness condition, where for every x belongs to L if and only if fx belongs to L prime, f of x belongs to L prime. We want the length condition where we want the length of mod fx to be bounded by some polynomial in length of x, and we want the domination condition as seen above. So the domination condition is very important, and without it, we'll sort of are like most of the properties we want out of average case reductions, they will not go through, as they will not be nice properties, so to speak. So now we proceed to prove a theorem. So now we show the result that if LD is average case reduces to L prime D prime, then L prime and L prime D prime is in distP, then LD is in distP. So since we have that L prime D prime is in distP, there must be an algorithm A which decides L prime efficiently efficiently under expectation, and then there is this constant C prime and epsilon prime such that for all m we have this expectation condition. This is the same as our definition. We've just replaced we just replaced 1 by c by epsilon prime, since there's other c's in the equation, just to avoid confusion. So f is the reduction we have from LD to L prime D prime, and we make A the obvious choice of the algorithm, where given input x, A computes f of x and then outputs A prime f of x. So by the regularity condition, no sorry, the correctness condition, A decides L, and all we need to show is that A is efficient. So that is, there exists a C and epsilon such that for all x the expectation condition holds. So now note that the time taken for A to compute some input x is the time taken to compute fx and the time taken to compute A prime of fx. Now we see that since fx is a polynomial in mod x, and for whatever value of time A prime fx it is at least 1. So we can bound this whole sum by h mod x times A prime x by choosing an appropriately large polynomial x. So I mean, we just need to make sure that the time taken by ax is bounded polynomially in mod x by the time taken by A prime on fx, which we can see makes sense. I mean, if you're confused here, just take a little time to see. Is just, since this is polynomial in mod x, and whatever this is, this it's at least 1. This is bounded by this is also at least 1. This is bounded by some large polynomial times this. So this inequality sort of works out. So we're making a simplifying assumption that f of x equals mod x power t, since we'll output strings of a certain length. But in general, even if we drop this assumption, things work out. We'll just make this assumption for the simplicity of our proof. So now we claim that for the expectation definition, the same epsilon prime will work. So we let epsilon equal epsilon prime, and we see that the expectation of the time taken is, this is just like unfolding the formula. So this is just taking the summation over all x, the probability that x shows up, times the time taken by A on input x to the power epsilon. So this is just the basic definition of expectation, and then this is less than or equal to less than or equal to this sometimes this quantity, as we saw above, this is bounded for some polynomial h. I mean, we've just replaced x by mod x by n for just convenience. And then we know that this whole quantity depends only on fx. Like this whole quantity for all x, we're only calculating fx. So what we can do is we can just group all terms where f f of dnx equals the quantity fx, and then we take the probability of that instead of fx, and we just plug that into the equation, and then we put we just instead of calculating over all x, we just calculate over all f of x such that this thing holds. I mean, we'll change the indices later, it'll just make sense. And this also works because, I mean, you can see why it works. If again, if you're just pause a little here if you need some time to see, but this sort of works out. We're just grouping terms here, not doing anything magical. So here we just, since we're still working over fx, we just make this an f and then leave an x here. So since fx equals y, we just replace this by, we replace x by y. If we're summing over the same things, we're just replacing over all y, where y equals f of d, where f of dn equals y, and then we just make a y here. Again, if that y doesn't appear, then the probability of f of x equaling that will just be 0. So we're not doing anything new. We're just changing variables, and the whole thing still equals the same thing, and we're not doing anything else. Now, here is where we use the domination condition. So the domination condition says, as we saw before, that given n, yeah, so the probability that f of x equals y is bounded by some polynomial qn times the probability that y shows up in the other distribution. So we use that here, and then so this whole sum becomes less than or equal to this sum, where this is qn, the probability that y appears in that the other distribution, the distribution d prime, times this whole term that we saw below before works because of this this thing that we claimed. So we just take out, since now we're taking the expectation over y, we just take out qn and all the terms that depend just on n outside, and then we'll just get summation ranging over the appropriate y's of the probability that y appears in the distribution d prime times the time taken by a prime on y power epsilon, and then outside this we have these two terms which do not depend on y being multiplied to the whole thing. So the other thing becomes the expectation. We can see that the definitions match, and then this is less than or equal to c prime h n this whole thing, because we see here that the expectation over a prime is, because of this condition we have this, for all m this is less than that, so this will be less than n. I think there's a typo here. This should be n, right? Oh no, this should be n power t. My bad. It's not a typo. Yeah, it should be n power t. So now all we need to. So this is not quite what we're looking for, but we can easily get the expected time is order of n from this. We'll just do that in an additional step. But I hope up till here it's clear, and then we'll move on. So here we have that if we use this using a small lemma, which is basically an inequality from probability which we used before while showing observation 3 previously. So let A be an algorithm for a distributional problem LD, and then say that this constant epsilon1, C1, and D such that this expectation holds, that this expectation is less than or equal to C1 n power D. And then we claim that there exists epsilon2 and C2 such that the expectation of the time to the power epsilon2 is less than C to power n. So we use this inequality that the expectation of something to the power to some power is less than the expectation of that thing to the power. This is a very standard probability theory inequality which we'll use. So we see that since this expectation is less than that, we just divide by n power d, since that's a constant to the distribution. So we just take that in, and then we raise the whole thing to the power 1 by d, and then the power d. This whole thing is less than what's inside the expectation to the power d. So this whole thing is less than equal to C1. Again, in case you're a little confused, it's just basic. It's just taking powers and taking expectations. This whole thing by this inequality is less than this, and this is less than C1 by our assumption. So we just have this inequality. We can remove this, and then we just raise it to the power 1 by d. So we have the expectation of time taken by dn times to the power epsilon 1 by d, which we now call epsilon 2 by n. It is less than or equal to c1 power 1 by d, which we call c2, and then we can take the n out because it doesn't depend on the expectation, doesn't depend on the n. I mean, it depends on the distribution, which is on n, but that's a different thing. So using this lemma, we have that this is less than or equal to c prime to the power n power d for some c double prime times n for some c prime and some different epsilon. We can make that if this whole thing holds, that this is less than equal to this, then this thing is actually polynomial time computable on average using this little lemma that we showed. So we have basically shown that this our notion of reduction is useful, since this is the sort of property that we'd expect, that if L prime D prime is easy and LD reduces to D, then L prime D prime is also easy. Where easy in this context means that the problem is in distP. So yeah, we sort of defined the notion of an average case reduction. Now we'll talk about completeness of problems, and Mohit will take over. Okay.
Now we have reached the final part of our presentation, wherein we will show there is indeed a complete problem for the class distNP. So we do this by defining a language, a rather artificial one, but yeah, a language which we call NBH, and a distribution U such that the pair NBH comma U is in class distNP, and given any other problem L comma D in the class, it can be average case reduced to the NBH comma U pair. So let's see what the problem NBH is and what the distribution U is. So NBH is the non-deterministic bounded halting problem. We've actually seen this in class at lecture 4. So what the problem is the language associated to the problem contains all pairs m comma x comma 1 power t, wherein M is a non-deterministic Turing machine that accepts X in at most T steps. In fact, in our class, we did show that this problem is NP-complete. In fact, this is the first NP-complete problem we showed in class. So again, recalling what we did, NBH is in NP because we can use a universal non-deterministic Turing machine to okay, first, given an input instance m comma x comma 1 power t, we can use a universal non-deterministic Turing machine to simulate m on x for t steps of m using like t power, like some polynomial t steps of the universal Turing machine. So hence we can use the universal Turing machine, run simulate m on input x for t steps of m, and then depending on the output, we'll know whether the whether the given string is an NBH or not. Hence, the language NBH is indeed an NP, and I mean this is not required, but anyway, another fact is NBH is NPR, which basically means, along with the first fact, that NBH is NP complete. So why is NBH NPR? Well, given any language L in the class NP, by definition of the class NP, there is a non-deterministic Turing machine, ML, which decides L in polynomial time, polynomial time. Now we can use the CARP reduction. That maps a string X to ML, comma X, comma 1 power P of mod X. So why is this indeed a valid CARP reduction? Well, given a string x, it say x is in L, then of course ML on input x in will be sorry ML will accept x in polynomial number of steps. And the converse is also true. If x is not in L, then the machine ML will not accept x in polynomial steps. So indeed, this reduction is a reduction which is a CARP reduction that makes NBH NP complete. All right, so this was a bit of a side note. Coming back, so first to show that NBH comma U is in the class distNP, we needed that NBH is an NP, which we have showed, and then we need U to be we need U to be P-computable. Well, let's see what the distribution U is. So the distribution U is somewhat of a roughly uniform distribution. We'll make that more precise. What do we mean by roughly uniform? Well, let's see. So to sample from the distribution UN, well, essentially n here is the number of is the length of the string, right? So to sample an element, what we do is we first pick three random positive integers a, b, and c, such that their sum equals n, right? And then once we have picked three random integers, we then pick a random string of length a and make that m, and we let m be that string, and then we similarly we pick another string randomly and uniformly of length b, and we let x be that string, and then we output m comma x comma 1 power c. So again, to repeat, we to pick a string of length n randomly, what we do is we pick three positive integers a, b, and c, and then we pick a string of length a, call that m, we pick a string of length b, call that x, and then we output m comma x comma 1 power c. The reason it's called roughly uniform is because we're uniformly picking we're uniformly picking a random string of length a, and we are uniformly picking a random string of length b. It's not exactly uniform because of we're doing a slightly different thing here, because we're first picking a, b, and c and doing something else. Anyway, coming back, so let's look at what the probability of a particular string exactly is. So it turns out, so how do we calculate this? So you see, first we are picking three random positive integers. That, if you think about it, that will contribute n choose 2 terms, which we are just denoting by this factor here. And then we are picking uniformly a string of length a, which will lead to this factor here. And then we're uniformly picking a length of string b, a string of length b, which will contribute to this factor over here. So hence, in total, the probability that the probability of this string appearing from the distribution un is essentially this quantity right here. All right. So indeed, it can be it can be shown that U is indeed P-computable, because this is a very well-defined thing, and one can come up with a Turing machine that quickly calculates the cumulative distribution function in polynomial time, and hence this U distribution is indeed P-computable, and hence the tuple we have defined NBH comma U is in distNP. Now, next we go on to show that this pair NBH comma U is in fact a complete problem for the class distNP. And to show it is a complete problem, well, what do we mean by a complete problem again? Well, let's see. We mean that given any distributional problem L comma D in the class distNP, we can find a reduction, an average case reduction from that problem to NBH comma U, right? So we're saying there is some reduction from L comma D to NBH U. So what will that reduction be? Well, that reduction is essentially a map from language L to NBH. Now we got to think of what that map should be. Well, we can ask, in the previous slide, we had written down such a map, right? From a language L to the language NBH. That basically that map was coming from the carb reduction we had. So the question is, can we use that exact map, that map which maps X to ml comma x comma 1 power p of x. So can we use this? So is this map, what I'm asking is this map an average case reduction? That specifically I'm asking, does this map satisfy the domination condition? Well, the answer is no, and let's see why the answer is no. Right. So assume that this map indeed, this map indeed satisfies the domination condition. Just assume that for now. If we assume that, then we'll be forced to. I mean, I'm just saying that this map will satisfy the domination condition only when we have for all strings x the probability of the probability of the string x appearing in distribution dn is lesser than or equal to this quantity here. So I'll show why this is the case in a few slides, but for now we'll just assume this. So I'm saying if this map satisfies the domination condition, then we definitely need, then we will, this will be true. That is, the domination condition is satisfied only when this condition is true for all x. Now, now it turns out this is false for many p-computable distributions. So why is this false? Like, let's see. If we look at this quantity here, in the denominator we have 2 power the length of string x, right? So when x, the length of x, so when we're looking at strings of large length, you see the quantity 2 power mod of x becomes really big. What that means is that this quantity here becomes really small for strings of large length. And now we are forcing the condition that the probability of x appearing through distribution dn is lesser than or equal to this small quantity, that is 1 over 2 power mod x. No, it turns out that, I mean, this really need not be true. Like, I mean, that's what I'm saying here. There are many p-computable distributions for which the above is false, and hence this doesn't satisfy the domination condition. So to just take the point home, I'll give an example. So consider the distribution D defined as follows. So it's defined as follows. So the probability of x appearing through distribution Dn is 1 half if x is the all zero string, and it is 1 half if x is the all one string, and it is 0 otherwise. So first of all, clearly note that this distribution is indeed p-computable, because just think about what the cumulative distribution function for this is, and you'll immediately realize indeed that that function can be easily computed in polynomial time. So this indeed is a p-computable distribution, and it doesn't satisfy this condition. Why is that? So look at this. What is this quantity? Okay, so we want this for all x. So I'll just take x to be the all zero string. So then we'll have the probability of the all zero strings appearing from distribution dn is 1 half by definition. Now note this 1 half is not lesser than or equal to, it really is actually big. It's quite large compared to this quantity if I make n sufficiently large. Because again, look at this. This quantity has 2 power n in the denominator, and if I make n sufficiently large, note the LHS is just half. It doesn't depend on n. But if I make n sufficiently large, the 2 power n becomes huge, and this whole quantity becomes really small, and of course it becomes much smaller than 1 half, and this condition is really not satisfied. So this naive, using this function does not give an average case reduction, because using this map, the domination condition will not be satisfied. So you might think all hope is lost, but we'll try to fix it. Let's see how we can fix it. Right. So this is the main idea of the entire theorem. So the idea is we had we were thinking of mapping x to this particular guy here. Now, the problem that arose was this denominator 2 power mod x. And the main issue was that 2 power mod x got really big for like x having large length, right? So now let's try something different. Let's map x to a different machine. uh, we'll come to what this machine is later on, NL, and instead of mapping it to X, we map it to C of X. Okay, and then we map the last part to one part some other polynomial in X. So okay, why might this work? Okay, yeah, thing is we will make this CX. So we have the liberty to construct it, right? So we will construct this CX cleverly. Cleverly meaning now note, we'll just, the main idea here is if, uh, so see again, this F again, just I'm recalling here, F satisfies the domination condition only when for all X we have this condition like before, except since we are mapping X to this C of X term here, you'll have 2 power mod of C of X, sorry, length of C of X instead of 2 power X as before. Now, the clever idea is this. So we construct a C of X, we construct a function C such that if this quantity, the probability of X is large, we'll make the length of C of X really small. Again, I'll repeat. If the probability of X appearing from distribution Dn is large, I will make I will ensure that the length of C of X is small. Why does that help? Well, if the length of C of X is small, that will mean 2 power C of X is also small. And that will mean this whole quantity as a whole will be small. So now if I make C of X sufficiently small, this whole quantity can be made large enough such that it indeed dominates the LHS. And if this quantity, say you're given a, if the probability of X appearing from distribution Dn is given to already be small, then we just let C of X be something like something that looks like X itself, because there's no issue there, because this quantity is already small, and like you don't need to make this quantity big anymore, right? So again, the idea is whenever the LHS is small, we make, I mean, sorry, whenever the LHS is large, whenever the probability of X is large, we make C of X small enough such that this whole quantity becomes big enough to dominate the LHS. So that's the main idea we're gonna deploy. And let's see. Right. So again, so I'm just calling this, we will soon construct an invertible compression algorithm. See, the reason why it's called a compression algorithm, like I told, so we're trying to make the length of C of X small, right? Especially we're gonna make it small when this quantity is huge. So that's what I've written here. So see, the size of C of X is small when this quantity is big, and the size of C of X is roughly the length of X when the probability of X is small. Okay. And of course, if we want this map to be a reduction, we of course want the correctness condition, right? That is, if X belongs to L, we really want n of L comma C of X of 1 part P prime of 1X to belong to NBH. So, what's the point if we lose the correctness condition, right? I mean, what's the point of coming up with a reduction which does not satisfy the correctness condition, right? So of course we would want C to be, I mean, NL, we want to define NL and C such that this whole thing is true. So I'll give you a quick idea before going into the details again. So what this the machine NL will do is basically as follows. So the machine NL, it look at C of X and it'll invert C. Invert meaning it'll take the inverse of this, catch hold of X from C of X, and then using that X, it will run ML of X. It will simulate ML of X on X and get the answer, right? So essentially NL just inverts this, like from C of X, it gets X, and it simulates ML on X and gets the answer from that. So that's the quick idea, and we'll indeed show that everything works out, right? All right. We'll show that in more detail now. This was just a summary. So let's start. What are the details we need to show? Well, the first detail I said I'll show is this detail. That is, if we use the the naive attempt, that is x maps to ml comma x comma 1 per this, that is satisfies the domination condition only when we have this thing, right? So I'll show why this is true now, right? So the first detail we're going to show is this. So assume f is the map, the naive map, which is it maps x to the machine ml comma x comma 1 power, I mean the string of all ones having length polynomial in mod x. Now say that map satisfies the domination condition. That is, there is a polynomial q such that for all y, this condition holds. Essentially, the probability of y appearing as f of x is bounded by q of the polynomial q times uh, the, the string y appearing from the distribution u itself, right? So assume this is true, right? Now let's see what that means. Now, because this is true for all y, I'll fix my y to be ml comma x comma 1 per p of mod x. Essentially, I'm fixing y to be f of x, and let's see what happens in that case. So first, note the easier thing. So the probability of f of x appearing as this when x is sampled through distribution d, and that's basically the probability of x appearing from the distribution dn. The reason for that is f is 1 to 1, and why is f 1 to 1 again? Just look at what f of x is. F of x looks something like this, and you can just read off x from this middle part. So hence this probability is just the probability of x appearing from d of n. Okay, so that's the left LHS over here. And what is this RHS? Well, let's look at this. Let's look at the RHS. So what's the probability of this string appearing from the distribution U? Well, remember how U was defined? Well, yeah, we remember, right? It was roughly uniform, and the probability of this, as we showed in a previous slide, looked something like this. Right? Okay. Now, using plugging this part in the RHS and plugging this part in the LHS, let's see what happens. So we get this over here, and if we look, this entire portion here, this entire portion is just a polynomial because q of x times a theta of 1 divided by some polynomial times some constant. That entire thing can be just thought of as a single polynomial, and what is left is 1 by 2 power the length of x. So, right? So hence, given the domination condition is true, we have this probability of x appearing from dn is bounded by this. And this is, as we argued earlier, might actually be false for many p-computable distributions, mainly because of the denominator here. So we have shown that this is not a good reduction. And as from the previous slide, if you remember, we had a different idea in mind. So let me get into the details of that. So what are the details we need to get into? So we need to show this map. So first, we need to define this map properly. That is, I have to tell you what NL is, I have to tell you what C is, I have to tell you what P prime is, and after I tell you all these three things, you'll have the map, and then I'll have to show that map satisfies all the required conditions of average case reductions. Okay, let's go one by one. I'll start by going to our function C, or another way to look at is our algorithm C. Let's see. Okay. Right. Part 2, the invertible compression algorithm C. Now, I won't give you the exact algorithm C itself right now because that's not really important. I'll just tell you the properties that we need from the algorithm C. So I'll state it as a lemma, and then later on at the end, I'll construct the algorithm C, and I'll as a proof of the lemma, I'll show that it will satisfy the properties we need. Right. So what are the properties we need from the algorithm C? Okay, let's go on. I'll just state it in the form of a lemma. Okay, lemma. Let D be a polytime computable distribution. That is, D is a p-computable distribution. Then there exists a polytime algorithm C satisfying the following properties. Again, just to emphasize here, D is a P-computable distribution. This plays a very crucial part in the proof, as we'll see the proof at the end. I mean, that was, you can say, this is the main reason why we needed. I mean, this is the only place where we are actually going to use the fact that uh, uh, problems in distP have P-computable distribution. So this is the crucial place we're going to use that, and it will be crucial in the proof of the lemma or the construction of the algorithm. Anyway, so what are the properties that the algorithm C satisfies? Well, the first condition, sorry, the first property says C of x. I mean, this condition is just telling us what C of x looks like. It turns out that this is not really important for us.
Did you
It's
mean dist
more
NP,
important in
by
the
the way?
proof. So we'll skip this for now. The next important property, which is very
Hello, can you hear
crucial.
me, Mohit?
Sorry.
Yeah, I said, did you mean dist NP? Like, I wasn't sure if I should interrupt you or not.
Oh, right, right. So wait, what did I say?
You said dist P, just a minor
Oh,
thing.
yeah, fine. I'll start this slide again, maybe. It's
No,
fine,
it's
right?
fine. We can go on. We can go on. It's fine. Like, errors are fine in presentations.
Wait, how do I stitch this together? You're saying we leave
Don't
all of
stitch.
this?
Don't stitch it. Like, yeah, yeah, it's fine. I'm sure sir will understand.
Okay, fine. Okay, so C will satisfy the following properties. Wait, where did I say? Okay, fine. C will satisfy the following properties. So right, C of x will look like this. This is the form of C of x, and this is not very important for us as far as the proof is the proof of the theorem is concerned. So let us look at the other important properties. The other property is C is one to one, or C is injective. That is, C of x equals C of y if and only if x equals y. We'll see why that's important. I mean, this is important while we are like inverting the algorithm C, or while we're extracting x from C of x. Okay. And the third property we need is the length condition. So remember, C is a compression algorithm. It's trying to reduce. I mean, we need the length of C of x to be small when the probability of x is large. So formally, I'm just writing it as follows here. So let's try to understand what's going on over here. So let's see. So this probability. So this thing over here, the small thing here, is the probability of x appearing from the distribution dn. Now, if that okay, case one is that is small. This quantity is small. Now, in that case, this 1 over that value will be large, right? So since this quantity will be large, when I'm taking the minimum, we'll just get mod of x. So essentially, the length of cfx will be some log x plus 1 plus mod x, right? So that's basically the size of x. But on the other hand, if we are given that the probability of x appearing from distribution dn is large, what will happen? 1 divided by that quantity will be small, and hence log of that value will be small, right? So hence, when we take the minimum, will the minimum will pull out, or will select out this value. So essentially, we have mod the length of cx is lesser than log x plus 1 plus this small quantity here. In essence, what I'm saying is, if the probability is large, then c of x is smaller than this small quantity here. Now, we'll formally see how that will all help out later on. Okay, so using these three properties, we'll finish the proof and proof of the theorem, and we'll leave the proof of the lemma to the end. Okay, going on to the next detail, that is the detail about what the non-deterministic Turing machine NL does. Okay, right. So let me just quickly show you. So right, essentially we're defining NL. NL comes over here, right? In this type of reduction we are doing. So I mean, intuitively, NL, like I told before, NL is just taking CX, it's inverting it, getting value of X, and running ML on that, right? So formally, I've written it out as follows. So NL, be a non-deterministic Turing machine, that on input n comma z does the following. It guesses a string x of length n. It guesses because it's a non-deterministic Turing machine. Now, once it guesses a string of length x, it computes c of x. and then it computes, and this computation can be done in polynomial time because C is a polytime algorithm. And once it computes C of x, it just checks whether C of x is equal to this input, right? And if it's not equal, well, that means it hasn't guessed the correct inverse of C of x, right? I mean, sorry, it hasn't guessed the correct inverse of n comma z, so it'll just alt and output 0. But then on the other hand, if 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 it guesses the correct inverse of n comma z, that means if it guesses x such that C of x equals n comma z, then it basically has inverted n comma z, and it'll use that. I mean, then it'll simulate ML on that input x, and it'll return ML of x, right? So again, I've just written out the thing I've been saying again and again. NL computes C inverse of n comma z by guessing, and then simulates ML on that particular value. Okay, now we'll make some observations. So observation one talks about the time it takes, I mean, the time taken by NL to do computation. So let's see. So what I'm saying is there is a polynomial P prime such that NL alts in at most P prime number of steps for inputs n comma z. Right, why is this true? Well, let's see. The first step, it's just guessing a string of length n. That'll take n steps, right? Okay. Next, it computes C of x. And we know C is a polytime algorithm and x as length n. So this whole computation will take some polynomial time in length of n, sorry, in n, right? And then the last thing it has to do is it simulates ML on input x. Again, ML is a polytime algorithm. I'm sorry, ML is a polytime non-deterministic Turing machine, and x as length n. So this whole simulation will take some polynomial time in length n. Sorry, in n. And hence, that's why there is some big polynomial p prime such that NL alts in at most p prime of n steps for an input of this type. Right, this observation 1 is telling us about the time of NL. Then we have observation 2, which talks about what, I mean, it just talks about what NL is really doing. Right, so what it's really doing, let's see. So NL accepts C of x, right? So C of x, again, remember, I mean, again, recall NL takes inputs of form n comma z, and essentially Cx is basically mod x comma C naught of x. So basically n is equal to mod x and z equal to C naught x, right? So NL accepts this pair in this large polynomial number of steps if and only if ML accepts x in the other polynomial number of steps. So let us orally see why this is true. Okay, so let's see the forward direction first. So say we are given NL accepts this pair in this big polynomial number of steps. Okay, what does that mean? Look at the description of NL. So because it accepts, that means it has come to step 3 and it returns this value, and this value is 1, right? Okay, that means it has guessed a string x such that C of x equals nz, where what was nz? Nz was the input, and what was the input? It was mod x comma C naught of x. So it has guessed a string x such that C of x indeed equals the correct I mean, I'm just saying NL has correctly inverted this C of x to get x, and then it has run ML on that input, and then ML has accepted x, and hence it has returned 1. That's the only possible way in which NL can accept 1. And hence, because of that, it follows ML also accepts x in P of x steps, because that's the only way we're getting 1 from the non-deterministic Turing machine NL. And note crucially over here, this direction only works if C is 1 to 1. Because if C was not 1 to 1, you could have guessed a different string x such that, say, I'll call it C of W such that C of W equals this pair, and then we'd really have ML of W equals 1 and not ML of X equals 1. So this forward direction crucially relies on the fact that C is 1 to 1. Okay, now going in the converse direction, say ML accepts X in this polynomial steps. Now if I give this input to NL, let's see what it does. So it can guess X such that C of X equals this correctly by just guessing the right string, and then it can simulate ML on that correct X, and then because ML accepts X, this ML will return 1, right? So hence indeed NL accepts this string C of X. So indeed the backward direction is also true, and hence we have our observation 2. Now let's so that completes the details of the Turing machine NL. Now we have all our pieces together. We have defined our compression we have the required properties of a compression algorithm. We have our machine NL, and we have our polynomial P prime. So we are ready to complete the proof, right? Okay, details part 4. Right. So let F be the map that maps X to the machine NL, to the string to the binary string representing the machine NL, comma C of X, comma 1, string of ones, string of P prime of mod X number of ones. And now we will show this indeed works as an average case reduction. Okay, first thing, P is polytime computable. Why is this? Well, NL is a fixed Turing machine, and C is a polytime computable algorithm, and P prime is a polynomial. So indeed, F is a polytime computable function. Right. So we have that. Next, length regularity. The size of f of x is the size of NL plus the size of C of x plus this polynomial. Now if you look, the size of NL is a constant. The size of C of x is well, what was C? It was a compression algorithm. It's trying to reduce the size. So of course, the length of C of x is indeed less than some polynomial. You can formally show it using this inequality we had here, but just from the name C compression algorithm, it's less than, it's polynomially bounded, and of course the polynomial is also polynomially bounded. So the entire length of f of x is indeed polynomial in the length of x. So that will give us length regularity. The next condition we want is correctness. That is, x belongs to L if and only if f of x belongs to NBH. Now, why is this true? Say x belongs to L. Well, by definition, we have if and only if ML accepts x in polynomial steps. Why? Why again? Well, recall ML was, ML was that non-deterministic Turing machine that decided L, right? So that's why we have this first if and only if. Now, using our observation 2, that is ML accepts x in this number of steps if and only if NL accepts C of x in this number of steps. Using that observation, we have this part is if and only if NL accepts C of x in this large polynomial number of steps. And then finally, this is equivalent, just recalling what how NBH was defined. This is equivalent to saying NL comma C of x comma 1 power the big polynomial belongs to NBH. So indeed we have a correctness condition. And finally, the only last remaining condition we have to verify is the big domination condition. Okay, what was the domination condition again? So we want to verify for all y, we want to show this inequality is true. Okay, let's go on showing it. Okay, uh, first thing, we want to show this for all possible y, right? Okay, now case 1 is if y is not of this form, like f is not of the form f of x, right? So if y is not of this form, that is if y is not of the form f of x for some x, then note this thing will become 0, because f of, I mean, if y is not of the form f of x, this event will never occur, and this probability is 0, and this inequality is trivially satisfied, right? So we are done in this case when y is not of this form, because this probability is 0 and this equation is trivially satisfied. So now we look at the other case in which y is of the form f of x, in the sense y is equal to nl comma c of x comma this one for some x. Now we've got to verify this condition for y's of this form. So let's proceed to showing that. Okay, now let us look at the LHS and RHS separately. Okay, what is the LHS? The LHS is this quantity right here. I've just put y equals this form as I've told. Now, now note that is essentially equal to the probability of x coming from the distribution dn. Now, why is this true? Well, because f is 1 to 1. Wait, why is f 1 to 1? Well, look at, well, what does f of x look like? F of x looks like this, and we can just look at the middle part here, c of x, and because c is 1 to 1, we can invert c, and hence we can get x, we can catch hold of x for it. So because c of x is 1 to 1, f will also be 1 to 1, and hence this equality holds. Okay, that's good. Now we look at the RHS side of it. The RHS side says what? The probability of this u star. Well, by star I mean uh, it's basically the length of f of x, right? Basically the length of this plus length of this plus length of this. It's too long, so I've just represented it as a star. Anyway, so what's the probability? I mean, what's the value of that? Well, it's just probability of u star equals this thing. And remember, from the definition of the distribution u, and as we had like shown it in the initial slides, it was this quantity right here. Now this is where we use our, so recall, so we use the first property of c to like the one-to-one property of c in the to show the correctness. Now we're going to use the length property of c in the domination condition as follows. So now note c of x, the length of c of x was smaller than this huge quantity, right? So because it's 1 over that, I'll get a greater than sign, and I've just replaced it by the small this quantity we had here. Now I'm just simplifying. So we have 2 power log x, that will come out as mod x, and then we have 2 power 1, that will come out as 2, and then we have 2 power minimum of this whole thing. Now note, we can just pick out, no, note, we can write that as greater than or equal to 2 power log of this, because there's a minimum here. So just think about it a little, you'll realize we can write 2 power minimum of this whole thing, I mean, sorry, 1 by 2 power minimum of this whole thing as greater than or equal to 1 by 2 power log of this quantity. And because we have 2 power log of something, that will just, the 2 and the logs cancel out, and we'll have 1 divided by p of thing, because we have 1 divided by 1 divided by this, so that this probability comes in the numerator. Now we are done. Like, why are we done? Well, let's see, let's look closely again. So we have, look at this quantity over here. So this quantity, this is just a constant, this is also a constant, this is a polynomial, and this is also a polynomial. So this whole thing is 1 over a polynomial, right? So now we let q of the polynomial q be equal to 1 over this whatever is in the denominator here, right? And now sending this thing to the other side, we will have, so recall this was this part. So we'll have this part plus this denominator polynomial q of n is greater than or equal to this thing. I mean, is greater than or equal to this thing, but which is the same as this thing, which is the same as this thing. So take a moment. If this is unclear, that's totally fine. Just take a moment, pause the thing, and you can easily see that indeed we have verified the domination condition with q, the polynomial q being this denominator over here. I mean, in fact, a quick observation here is that this is the first time we are actually using that uh, using this fact, this polynomial room, this room over here, because if we didn't have this in our definition for our average case reduction, this argument wouldn't go through, right? So that was the reason for giving a small polynomial playroom such that we could fit everything inside it and make sure everything works out. Okay, to just recap, so we have done this reduction. I mean, we have defined our reduction as like as this, and we have shown the three conditions that we need to show f is the average case reduction, and hence we have an average case reduction from x from, I mean, this is an element of L to NBH, and hence indeed L reduces, and average case reduces to NBH, which indeed shows that the the distributional problem NBH comma U is a complete problem. So that completes the proof of the theorem. Well, except we have a small detail left, that is proving the proof of the lemma, that is constructing the compression algorithm. So we hope you're convinced with the theorem. Well, save the construction of the compression algorithm, which we will now do and finish our presentation. All right, coming back. So this is the lemma we wanted to prove, in which we basically construct our compression algorithm. Okay, let's begin. So, uh, so our algorithm will, on input x, will output a pair, the length of x, comma, c naught of x. So c naught is another function. Okay, quickly, the whole reason for having this the whole point of having this value in c of x was to ensure c is injective. Now, if, I mean, going through the proof, you'll realize that c naught is injective, but it is only injective on inputs of the same length. In the sense, c naught is not injective if you give it values of different lengths. But then we wanted C to be injective, and hence we put in the size of X to make C of X injective. This will all be clear soon enough. So we go on. So we first define C naught of X as follows. So let C naught of X, recall what we wanted to do. We wanted C of X to be a string, a small string when the probability was I, and we wanted C of X to be basically a string of roughly X when probability was low. So that's what we do here. So we define C naught of X to be 1x. What do we mean by 1x? Well, it's just the bit 1 concatenated with the binary representation of x. So it's just 1 followed by the bits of x. So let C naught be 1x when the probability is small, specifically when it's lesser than 2 power minus length of x. And when the probability is large, here we let it to be, so we want C naught of x to be small, right? So we let that to be 0 concatenated with h of x. Well, what is h of x? Well, h of x is a polytime computable function such that h is 1 to 1 on inputs of the same length, and h of x has quote unquote small length, right? So let's see what exactly this function h is. Okay, right. Now, to construct this function h, we crucially rely on the fact that d is polytime computable, as I've been telling uh, in the previous slides, right? So now let mu n of x be the cumulative distribution, that is specifically uh, it's the probability of the event dn less than x. So let that be the cumulative distribution function. And now let h of x be the longest common binary, okay, longest common prefix of mu of x and mu of x minus 1 when both are written out in binary. To repeat, take mu of x, write down mu of x, write down mu of x minus 1 in binary, like in binary, and look at the common, look at the common prefix after the decimal point and take the longest common prefix, right? Let that be h of x. Okay. Now let's see how that helps us at all. Okay. So yeah, given our definition of h of x, we'll make some observations about the function h. So first note, h of x is polytime computable. Why? Well, uh, well, because the distribution dn was polytime computable, one could compute its cumulative by definition of p-computability. One can compute the cumulative function distribution function. I mean the cumulative distribution function at point x in polynomial time, and similarly this value in polynomial time. And one could, looking at that, one could take the largest common prefix in polynomial time. So that will tell us h is polynomial time. The other property we needed of h is 1 to 1, and let's see why this is true. Okay, so say, I mean, okay, so again, a quick clarification here. H is not 1 to 1 on all inputs. It's only 1 to 1 on inputs of the same length. Again, I'm just emphasizing this because it is not 1 to 1 if you give it two inputs of different length. All right. So now say h of x1 equals h of x2, and that is some string s. What is s again? I mean, s, you see the definition of h of x, s is the longest common prefix of mu of x and mu of x minus 1. Okay, so okay, let's see. That will mean, okay, let's just look at x1 for the moment. So s is the largest common prefix of mu1 of x and mu1 of x minus 1. So how will they look like? Let's see. So mu1 of x minus 1 has to look like this. So it will look like 0 point, the string s followed by 0 and then star star star, where star 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 can be uh, something. And then mu n of x1 will have to look like 0 point, the string s 1 star 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 star. I mean, look here. So the longest common prefix over here is s. Now you might ask, wait a second, why? I mean, the only information we have is the largest common prefix, and how do you know this is a 0 and this is a 1, right? Well, let's see. What we know is that after s, the bit year and year have to be different. That means one of them has to be 0 and the other one has to be 1. But we know that this mu n is a cumulative distribution function, and hence it's monotonic, right? It's monotonic, and by that monotonic, because x1 minus 1 comes before x1, it has to have a smaller value. Hence, if I give 1, if I put 1 over here and put 0 over here, that'll contradict the monotonicity of mu n. So it has to be 0 over here and it has to be 1 over here, and thus these have the two forms I've told. Okay, now we also add, recall, we also add h of x2 to be the same string x, and by the same kind of logic we have used, we'll have the same kind of thing going on here as well. So essentially mu1 of x2 minus 1 looks exactly like mu1 of x1 minus 1, and mu1 of x2 looks exactly like mu1 of x1. Now, again, to emphasize, the reason why we wanted inputs of same length is because we wanted mu n, like mu that n to be the same here. Because if n was different over here and here, we really, I mean, the argument we're going to give now will fail. Okay, that's just a disclaimer. Okay, coming back, right, now we see, as mu n is monotonic, okay, as mu n is monotonic, observe that this value is smaller than this value. Hence, by monotonicity of mu n, we'll have this x minus 1 is strictly lesser than x2. And similarly observe, this value is smaller than, strictly smaller than this value. And by monotonicity of mu n, hence we'll have x2 minus 1 is strictly lesser than x1. Okay, now just looking at this, just staring at these two things for a couple of seconds, you'll immediately realize this can only happen when x1 equals x2, from which it follows h is 1 to 1. So that's the second observation about h. And the last observation to finish it all, is talking about the length of h. Okay, now we claim that the length of h of x is lesser than or equal to the log of this. Let's see why this is true. Let's prove this by a contradiction. Right. So now assume for contradiction, the length is actually bigger than this quantity. Now what does that mean? That means the longest common prefix of mu n of x and mu n of x minus 1 as length at least this. So that means just looking at here, this s as length at least this huge quantity here, right? So what does that mean? If I take that difference, so essentially I'm subtracting this minus this. So if I subtract this, see what happens. You'll have 0 point. So since S and S are same here, you'll have 0.00000. How many zeros will you have? Well, uh, you'll have the number of zeros will be the length of S. And sorry, the length of S is mod of, I mean, the length of h of x. So to repeat, you'll have, so since you'll have at least mod x number of zeros, mod s number of zeros, the quantity has to be less than this, less than 2 power minus uh, the number of the length of s, and the length of s is uh, uh, length of h of x, which is greater than that, from which you get the difference has to be less than, strictly less than, in fact, 2 power minus this quantity here. And just taking the minus sign inside and cancelling the 2 and the logs, we get this. Now, but note, wait a second. Mu n of x minus mu n of x minus 1, well, that's just the same quantity here. So we're getting a quantity is strictly lesser than the same quantity. But that's, of course, a contradiction. And hence, we have that this quantity is, the length of h is indeed bounded by this sort of a quantity here. And that indeed completes the proofs. What exactly do I mean? Well, again, let's just recall c of x was mod x times c naught, and c naught was 1 of x times 0, 1 of x, sorry, 1 concatenated with x and 0 concatenated with h of x, depending on the condition. Right. So again, I'll quickly say why this works again. Uh, so again, c is, first condition we wanted, c is 1 to 1. Oh, sorry, that's not the first one. First condition we wanted, C is polytime computable. Well, because each thing over here is polytime computable, right? So h of x is polytime computable. Writing down all of these is polytime. It can be done in polynomial time, and C of x is polytime computable. That's the first thing. Second thing, C is 1 to 1. Why is that the case? Well, assume uh, assume you have two x1, x2 such that their uh, their output is the same. Now, looking at this first bit of c naught of x, we can split into the two different cases. And in this case, because it's just x here, we can immediately get x1 equals x2. And in the other case, wherein it's c naught starts with a 0, we'll have h of x1 equals h of x2. But we'll also have mod of x1 equals x2. And because of this second observation here, we'll get x1 equals x2. And hence, indeed, like this second observation and followed by the clever construction tells us that C is 1 to 1. The final and last condition is about talking about the length of C, right? So if you notice, let's see. So in this case, the length of C of x will be, well, the length of this, which is log of mod x, plus this length of this 1-bit string plus 1, plus it's lesser than x, right? I mean the length of x. So indeed this is satisfied for the first case. In the second case, again, the length of C of x is lesser than the length of mod x, which is uh, log of mod x, or probably yeah, length of mod of x plus the length of the 1-bit string 1, I mean the length of the 1 bit which contributes 1 here, plus the length of h of x, but the length of h of x is known to be lesser than this quantity, right? And hence we get this inequality. So indeed, as we have claimed, we have a polytime computable, uh, a polytime computable algorithm C which satisfies these three conditions, which hence proves the lemma. And hence, because the lemma is proved, the theorem goes through, and indeed we do have an artificial, I mean, complete problem in the class distNP. So this completes our presentation about average case complexity, and this is where we end. Thank you.
Yeah, thank you.